So we've all been there. A car in the workshop with a headlight, indicator, blower motor, or any other electrical component not working. Where do we start? DTCs? Power? Ground? Or do we just throw parts at it until the problem goes away? Of course, the answer will depend on the diagnostic strategy we use. But at some point, we need to check the power and ground circuits to see where the fault has occurred. We also need some idea of the best tools to use when checking these circuits. Let's start with a common workshop occurrence. A vehicle is presented with an inoperative headlight. 9 times out of 10, it's just a bulb, right? But what do we do if we replace the bulb and the headlight still doesn't work? We need to check the power and ground circuits to determine where the fault is. And the most effective way to do this is by looking at voltage drop. So why can't we just use a test light? They're simple, easy to use, and I've got 4 of them in my toolbox. Well, the simple answer is that a test light will illuminate even if there is a very small voltage present, and it cannot tell you how much voltage is present. The multimeter is the best tool for the job. It's very accurate, easy to use and read. The reason we use a voltage drop check is because it can clearly identify opens and resistance faults quickly. Voltage drop occurs when there is excess resistance in a circuit, like a corroded battery terminal or poor terminal tension in a connector. Source or battery voltage is available to one side of the connector. In this case, the poor contacts cause a resistance, and a much lower voltage is seen after the connector. To measure voltage drop accurately, there must be current flowing in the circuit. In other words, it must be in operation. Set the meter to volts DC and place the red lead on one side of the connector and the black lead on the other. What we have done is create a parallel circuit using the digital multimeter. The voltage that cannot pass through the resistance, or poor terminal contacts, is instead displayed on the meter. So we can see that this connector has a drop of 2 volts. If our circuit has multiple connectors with multiple poor connections, then the sum of all voltage drops may be enough to render the circuit inoperable. The great thing about a voltage drop test is that it can be performed on power and ground circuits. So now that we know what voltage drop is, we need to know how much is acceptable. Some manufacturers will give you values for different circuits or cable sizes. But the easiest way to determine if a connector or junction has too much voltage drop is to use the go, no-go method. When performing any voltage drop test, select the millivolt scale on the meter and perform the check. If the voltage drop is equal to or less than 300 millivolts, the value will be displayed on the screen and is acceptable. This is the cue to go or continue testing at the next connector in the circuit. If the meter displays OL or overload, the voltage drop at that connector is equal to or above 400 millivolts. OL is a no-go trigger. This means that the voltage drop at the connector is not acceptable and needs repair and retesting before moving to the next connector in the circuit. Okay, so let's perform some voltage drop checks on a real workshop problem. Our customer has asked us to replace the headlight bulb in their car. I'll remove the bulb and check it on the bench. Well, it works okay here, so that means we have a fault in the headlight circuit. Let's refit the bulb and then check out the circuit diagram to locate our power and ground circuits and then plan our test. This diagram is a little busy, so we'll need to peel off everything except the circuit we want to test. Now that we have a very simple circuit, we can see a positive voltage supply at the top of the page, flowing through the switch block, fuse assemblies, then to the headlight. The ground circuit is on the lower side of the headlight assembly. We can't assume where the fault is, but we can perform some voltage drop checks to point us in the right direction. If the globe isn't working when plugged into the circuit, but is okay on the bench, our fault may lie in the switch, fuse, wiring, connectors, or ground point. Common sense tells us we should check the easiest bits first. And since we're already at the headlight, we should check the globe connector first. Turn the headlights on. Switch the meter to volts, DC, and then place each lead on the back of the connector terminals. In a correctly operating circuit, we should see a volt drop equal to the source. Again, we are measuring the voltage consumed by the globe. If we see the correct voltage and the globe is not illuminated, the fault must be excess resistance or an open in the globe socket. Think corrosion or poor terminal tension. But if the meter reads 0 at this point, then we're missing a power or ground supply to the socket. This headlight has another connector at the rear of the housing that may cause our fault. Again, let's check for voltage drop across the supply and ground circuits. In a correctly operating circuit, we should again see source voltage, as this is what is consumed by the bulb. But if the meter displays substantially less, or 0, our fault lies outside of the headlamp assembly, in either the supply or ground circuits. So far, we've spent very little time on this job, and we need to keep it that way. Our circuit diagram shows that this circuit is supplied by fuse F20. Our next voltage drop tests are across conductors, not consumers, so we can perform our go and no-go checks. Turn the headlights on, locate the fuse, and select the millivolt scale on the meter. Place the leads on the back of each fuse terminal while watching the meter display. If the meter value is OL, then we have a no-go situation, which is in effect substantial voltage drop across the fuse or fuse terminals. This could be due to an open fuse or poor contacts due to corrosion or insufficient terminal tension. If the value displayed is less than 300 millivolts, then we have a go trigger and can continue our circuit checks. Our next voltage drop check should also be a quick one. We need to narrow down the search area a little bit. We should now perform a volt drop check between the fuse, remember we have proved that this one is okay, and the battery positive post. If the meter value displays OL, then this is a no-go trigger, indicating the fault is in the upper section of the circuit. If this is the case, we can stop our testing here and then explain to the customer that we've located the fault region. Because it includes the battery harness, instrument harness and fuse box, we need to dedicate some billable hours to the task. If they agree, we can continue our go and no-go checks until we locate the fault. My best advice at this point is to keep 1 meter lead on battery positive and keep moving the other back towards it, checking each junction and connector until the meter value shows less than 300 millivolts. Right, so let's back up a little and imagine there's no voltage drop between our battery positive and the globe socket. This only leaves the ground circuit for the headlight assembly. Just follow the same rules to perform a volt drop check on a ground circuit that we just did on the voltage supply. Connect the meter between ground point EP5 and the globe socket. Turn the headlight on and watch the display. A no-go trigger indicates an open or excess resistance. We can check the ground circuit between the bulb and the headlight connector, and even between the harness and the body ground point. This type of circuit testing is fast and accurate. We can perform voltage drop checks on any circuit within the vehicle and determine if that circuit is good or bad. Remember to group your checks to speed up the process. If we're at the headlight connector checking the voltage supply circuit, we can also test the ground circuit at the same time. Don't get bogged down with simple faults. Perform voltage drop checks and be confident with your diagnosis. That's all it takes. Keep training. Thanks for watching.